Hello, everyone. In this presentation, we will talk about our paper, which is dimensional analysis for multidimensional data flow programming, prepared by Bill Wage and myself, Monem Shennat. I think some of you guys are not familiar with data flow programming language or Lucid programming language. So under introduction, I'm going to talk or give you an idea about Lucid programming language and its statements. Then I'm going to talk about multidimensional data, dimensional analysis, or an example of dimensional analysis, our main objective, and then data flow operators, dimensional analysis algorithms, conclusion, least but not last significance. Lucid is our prime example. It's a functional language in which every data object is a stream, which is a sequence of values. All Lucid operations map streams into streams. Therefore, a program in Lucid is simply an expression together with definitions of the transformations and data referred to in the expression. It can be considered as a data flow language in which the variables or the streams name the sequences of data values passing between the actors, which correspond to the functions and operators of the language. Lucid programs do have statements, which are equations specifying the transformations to be applied to streams. For example, if we say is equal r sum of x, which means running the summation of its argument. What about multidimensional data? As we have many multidimensional data base systems, as well as OLAP systems, which are also based on a multidimensional model, it can happen that some dimensions may actually not be needed to specify values in a data set, as well as we will see in the example next slide. Granular Lucid or GLUE was a dialect of Lucid that allowed multiple dimensions. So GLUE is multidimensional language where the value of expressions need to embedded context, which is captured by a group of dimensions. However, it's dimensional analysis that was primitive because GLUE used a simple-minded case analysis of arguments of user-defined functions. Now, this example shows 6 dimensions for X-ray image, where each pixel is determined by horizontal dimension, vertical dimension, z-dimensional dimension as backward, forward, time dimension, patient dimension, and date dimension. It's obviously that relevant dimensions as are xi if they are if this image for only two dimension, and the time if it's not video. Nevertheless, this example is very simple and use just X-ray dataset. But in order to be our idea clear for dimensional analysis of multidimensional data flow programming, we need to figure out which dimension is relevant to the stream's dimensionality. So our goal is to create an algorithm for dimensional analysis of a multidimensional um, dialect of the data flow language, Lucid, that allows us to calculate the dimensionality of program variables and to exclude irrelevant dimensions. So, what are the operators in Lucid? In addition to the basic operators that we can see in almost every equation, such as plus and minus, Lucid also um, Lucid also has operators like these four basic operators: first, next, as soon as, and followed by. Let's know more about these operators. Um, so this figure shows a simple data flow network which produces in order the sequence one, two, three, 5, 8, etc. as a Fibonacci numbers. These nets are continuously operating devices. This network explains the use of several important nodes, which are the operators in data flow programming language. So the one consider, for example, the one considers plus that matches to ordinary operations on data items. The plus node frequently waits for the arrival of tokens on its input lines. And then the moment that there are tokens on both lines, a token represents the sum of two tokens, which then that sum is sent down the output line. The node labeled 2 simply produces an endless stream of tokens representing the number 2 or representing the number 2. But the remaining nodes do not process tokens, but just operate them. For example, the next node rejects the first token, which arrives but passes the rest on. However, the followed by node locks out for the first token to arrive on its left input and pass it on as its first output. But after that, pass on whatever appears on its second input line. Now, going back to the four basic operators because I will use them to explain our algorithms in these next slides. So what does first operator do is send on the first item in its input stream, and sort passes the rest. But the next operator skips the first and passes on the rest. However, followed by operator, the output of this operator is the first component of its first input, followed by its entire second input. As soon as operator, for this one, the value of the first argument has when the second argument first becomes true. Dimensional analysis algorithms, as it's shown here in this slide, we proceed incrementally by the following stages, from simplest to more difficult, from one dimension, which is the time dimension, to multi-dimensionals. Well, let's explain more for time dimension. The first in this example that shows some data flow equations which have different Lucid operators, and after n times of iterations, we first speculate that all the variables are constant in time, and then we repeatedly reevaluate these guesses depending on the equation defining each variable. For example, the first one, or the first equation, which is A equal B plus C, then A varies, that means A varies in time if B or C does. However, for example, J equal 1 followed by K means J varies in time. Consequently, the equations which have relevant time dimension are J equal 1 followed by K, and then I equal 1 followed by M. This is because J and I in those equations vary in time. Also, in the next iteration, we have the equation M equal I plus 1 has relevant time dimensions. Why? Because in the previous iteration, we knew that I varies in time. The second algorithm, Lucid with 2 dimensions, space as well as time dependencies. So there are four, for this algorithm, there are 4 possibilities. The first one, space and time, if the variable depends on both dimensions, space and time. Then space if it depends on the space only, and then the time if the variable depends on only time, and for constants is empty set. Actually, we repeatedly assign a subset of space and time to each variable as set of dimensions to which variables are sensitive. For example, in these equations, B doesn't have any relevant dimension for those possibilities or for those four possibilities. However, there are three possibilities for the variable Q, which is sensitive to space dimension, sensitive to space and time, and again, sensitive to time and space, plus the empty value, which is sensitive to non-dimension. Now, the most important algorithm, which is for multiple dimensions, based on using the operators in the algorithm of two dimensions, we discovered a new model or which is listed in these streams. Therefore, the algorithm for multiple dimensions is more complex than the second one. In this algorithm, there are unlimited sets which can be accumulated in such a table which assigns to each variable a set of dimensions based on how many times this variable will be re-evaluated. Then this also can have from only a constant which has no dimension too many dimensions which are relevant to that stream or variable. This flowchart shows the analysis steps for multi-dimensions algorithm. So after the first evaluation or approximation, we can do the re-evaluation from 2 to n times until there are no further changes of these multi-dimensionalities. So in this table, some DA equations for multidimensional algorithm. Those are atomic equations that we need to do an evaluation for each equation to know the dimensionality for every stream. Then we can figure out how many approximations and which dimension is relevant in every approximation. For example, in the first equation, we have y equal each followed by c dimensionality of v. So the dimensionalities reevaluation is that wise dimensionality is the union of those of H and V dimensions plus C dimension. Consequently, the first approximation of the relevant dimensions is antiset, as we can see in the first or under the first approximation. Then there is no relevant dimension for of course for this empty set. Nevertheless, the rest of approximations depends on how many times that we can reevaluate that stream based on the dimensions which are relevant to the stream. And the sequence of those streams are in a data flow system. As a conclusion, we have algorithms to estimate the dimensionality of programs which are one dimension, then 2 dimensions, and multiple dimensions. What remains is to analyze programs with users-defined transformations. For example, run sum of x equal s, where s equal first x followed by s plus next x. That we will talk about it in much more details for our next paper. The significance, our DA algorithm will make possible the efficient implementation of multidimensional Lucid. There are some platforms like TensorFlow needs to know which dimensions are relevant, and currently this is the user's responsibility. Thank you for listening, and I hope that I know there are a lot of information and it's a kind of complicated topic, but I hope that I gave you guys an idea about what's going on. So back to now, back to the host, and thank you so much, and bye.
Okay, thank you, Monem, for your talk. Please, let's give him a clap through our emojis here, and please raise your hand to ask questions or post your questions in the Q&A session. So, Peter, I will hand you the floor so that you can ask your question.
Yep. Okay, yes. Hi, Monem. Thank you for your presentation. Pre-recorded and all. I have to confess, I've really felt the last sentence in your presentation that you said, well, there was a lot to take in, and I'm absolutely no Lucid expert. In fact, this was the first time I actually saw these kind of things. So I was trying to make a mental model out of your presentation. So I got a bit puzzled by these equations. So at early on in your presentation, you had this equation A equals B plus C. And you said that means that you generate a stream A, which value changes as soon as a value in B or C changes, right?
Yeah, so if one of these values varies in time, so we can say that A varies in time, for example.
Yes.
Otherwise, they will be all like irrelevant dimensions or none. It's kind of a constant. So we will consider that as irrelevant dimensions to the data.
Okay, so you say constant, because that would be my next question. Because you also had this equation in the form of A equals B plus 1. I was wondering what this one value is. Is that a stream of one values, or how should I interpret that? I actually put it in the Q&A tab. Perhaps you can have a look at that. It's always easier to read it rather than try to explain it orally.
Yeah. Well, let me just. So we have A equal B plus C, and we have M equal I plus 1.
Yes.
So I think you are talking about M equal I plus 1, isn't it?
Yeah. I didn't know. I didn't remember what the equation exactly was, but yeah.
Yeah, that's fine. So because we have kind of iterations for our algorithm. So I in other equation, I equal 1 followed by M. And followed by is an operator in Dataflow programming or Lucid program that push the network or the data to give an input. It's kind of operator that generate the sequences. So that's why when we say I equal 1 followed by M, so we will consider like I is already varies in time, and then in the next iteration, when we back to that equation, which is M equal I plus 1. So because I it's already varies in time, so we can say consequently we can say M is also vary in time. I hope that's clear.
Not yet.
It's all about the operators that you use for Dataflow programming language.
Yes.
So because and it's kind of in order for these sequences. So so as long as you are using follow by operator, everything will come after that in these iterations will be almost. I mean, it will be it will be changed. I mean, we will consider that a variable or a stream changes in the dimension. So we define that as relevant dimension.